right, let's take a look at section 4.3. So we're continuing our discussion with derivatives and how they can be applied. And we're going to start moving into looking at graphs of functions. So make sure your cell phone is put away. I'm going to give you some definitions and some rules here that are really important. We're going to use quite a bit over the next few sections. So make sure you're taking good notes and following along. I want to start off by talking about where a function would be increasing and decreasing. And at this point, it's extremely important that you make the distinction in your mind when you're discussing f versus f prime. Those are different functions with different characteristics. And what we want to do is be able to establish the relationship between f and f prime, for example, and note what one tells us about the other. So we're going to start off by looking at f as a function, knowing that it is continuous and differentiable on the interval a to b. Whether it's closed or open is not quite as important, but here's what you want to remember. If f prime of x is negative for all x in that interval, so if the derivative is negative in a given interval, that tells us then that f is decreasing in that interval. And that should make sense. Here's a graph of f. Notice that over this first interval, f is decreasing. That means our slopes are negative, right? If I were to draw tangent lines, the slopes would all be negative. So that should be intuitive, I think, by this point, that the first derivative would be negative in that interval. Likewise, if the first derivative is positive over a given interval, then that tells us that the function is increasing. So over here on this graph, you can see the opposite is true. F is increasing. Notice that the slopes of the tangent lines would all be positive over there, and that's what that tells us. And then finally, if f prime of x equals 0 over a given interval, then that means f is constant. That means we're looking at a horizontal line, right? The derivative would have to be equal to 0. So number 1 says, find the intervals over which the function is increasing or decreasing. Now, the first thing to remember is a function is going to change increasing and decreasing, or vice versa, wherever we have a critical number. So the first thing you want to do is find critical numbers. That's always the first job on these questions. So I'm going to take the derivative. Remember what a critical number is. It's where the first derivative either equals 0 or is undefined. In this case, we have a polynomial, so I don't have to worry about where it's undefined, but it is going to equal 0 at a couple of locations. I'm going to factor out a 3x here, so I have x minus 1 equals 0. And I have two critical numbers for this function, 0 and 1. And then what we're going to do is we're going to do what's called a number line analysis. And we've seen this off and on here and there, but we're going to be a little more formal about it. You're going to draw a number line. You're going to label your critical numbers. Those are the only numbers that go on your number line, because like I said, if f prime is going to change signs, it's going to do so at these critical numbers. Or rather, if f is going to change from increasing to decreasing or vice versa, it's going to do so at these critical numbers. So I'm going to label this f prime, get in the habit now of doing that. Label your number lines. This is f prime because later on we're going to talk about f double prime. And then what I'm going to do is I'm going to choose a test point. So in each interval, I'm going to test out a number that's in that interval, and I'm going to plug it into f prime to see whether it's positive or negative. So let's say I test out negative 1. If I plug negative 1 into f prime, I don't even care what the number is. I just care whether it's positive or negative. Personally, I find it helpful to use the factored version of the function, the first derivative, to do my test points. So if I plug in negative 1 into this factored version, I'm going to get a negative number in the front and a negative number on the inside. So a negative times a negative is a positive. And so that entire interval f prime is going to be positive. In between, let's say I test out 1/2. If I substitute 1/2 into the first derivative, I'm going to get a positive times a negative, which means I'm negative in that next interval. And then I'm going to test out, in the last interval, let's say we test out 2. If I plug 2 into the first derivative, I get a positive times a positive, which means I have a positive. And actually, I have a picture of the graph here so you can see what I'm talking about. F starts out increasing. This is a graph of f, by the way. increasing until we get to 0, then f switches to decreasing until we get to 1, and then it switches back to increasing. So here's what you're going to tell me. This is what I would want for your answer. You're going to tell me f is increasing on the intervals negative infinity to 0, and then again from 1 to infinity. And I need a reason for this, so you can say because f prime is positive. I want you to give me a reason for that in that interval. And then you can say f is decreasing in between in the interval from 0 to 1, and you're going to say because f prime is negative. Okay? And so you want to use the numbers in your critical numbers, rather, nothing in between. You don't want to use your test points to label these or anything like that. The critical numbers are where things change. So make sure everything is covered. Negative infinity to 0, 0 to 1, 1 to infinity. And that's the answer to the question they asked. A function is said to be what we call monotonic. So that's a fun word. Monotonic on an interval if it is either increasing or decreasing on the entire interval. So as an example, this is the graph y equals x cubed. Notice that it's increasing the entire time. This would be the exponential function. I think it would be e to the negative x, if I'm not mistaken, or something along those lines. And that would be decreasing the entire time. So let's take a look at what this leads us to. Where is this headed? This leads us to something called the first derivative test. So the first derivative test is used to tell us where we have local maxima and local minimum. Remember, I used previously this term and I said local and relative are used interchangeably. Same thing. So it says, let C be a critical number of f. So we're going to find critical numbers the same way we always have on an open interval containing C. As long as the function is differentiable on the interval except possibly at C, no big deal, just roll with me here, then f of C, if f prime changes from negative to positive there, that tells us that f of C is a local minimum. So we're talking not about the interval, we're talking about the point at f of C. We have a local minimum. On the other hand, if f prime changes from positive to negative at that location, then we have a local maximum. And those definitions, I think, are somewhat intuitive if you think about increasing and decreasing and what this tells you. If f prime changes from negative to positive, that means that f changes from decreasing back to increasing at that location, if that's C. So if we're looking at this on a graph, maybe this would be C, then that would mean we have a local minimum, right? And then on the other hand, if f prime changes from positive to negative, what does that tell me about the behavior for f? Well, then f goes from increasing back to decreasing at C, which means we have a local maximum. And so that's where those definitions come from, and that's how the test works. Very quickly, let me go back to this example, and I didn't ask you this previously, but had I asked you this, you would have told me that at x equals 0, so if you want to add this to your notes here, let me use a different color. At x equals 0 in this example, we would have had a local maximum. And the reason is because f prime changed from positive to negative at that location. And that's what we see in the number line, positive to negative, and that change occurred at 0. On the other hand, at 1, f prime changed from negative back to positive. So we would have said at x equals 1, we had a local minimum, and you can see that in the graph. There it is, right there. There was our maximum, there was our minimum. A local minimum because f prime changed from negative back to positive. And so this number line analysis is very important, and we're going to use this to say where a function is increasing and decreasing, as well as to run this first derivative test and determine where we have a local maxima or minima. So bring your notes with you, and I'll see you in class.